Hello everyone. Here yet again we are going to discuss an application of the Ampere Circuital Law. We are actually going to find the magnetic field at a point due to a toroidal solenoid. It is also considered or named as toroid only, or we can also say it to be toroidal solenoid. Now, what exactly is a toroid? If we take a long solenoid and if we bend it in the form of a ring, then it becomes a toroid. Now, when current passes through the wires, which is in the shape of a toroid, so magnetic field is produced. So we are going to derive the relations for the magnetic field using the Ampere Circuital Law. So let us see how it is done. First of all, let us consider what exactly the toroid is. This diagram shows a toroid. It is also considered as toroidal solenoid. You can see here the turns which are shown here. They are a part of a long solenoid only, but they are bent in the form of a ring. So when current passes through it, magnetic field is produced, and we are going to derive the relation for the magnetic field. Now, this is a sectional view of a toroid, and the section is in the plane of the paper. Now you will find the dots here. These dots, they actually represent the current coming outward, and whereas the cross represents the current going inward. So it is the section of the toroid which we are considering, and that section is actually parallel to the plane of the paper, where the dots represents the current which is coming up, that is outward, and cross represents the current which is going down, that is inward direction. Okay, so here you see we have actually three different positions where we are going to find the value of magnetic field. One is the interior of the solenoid, one is inside the solenoid, and the last one is at the exterior of the solenoid. That is the points which we are going to consider. One is at the interior, another is inside the toroid, and the third point will be outside. So naturally the Amperian loop, because we are going to use the Ampere Circuital Law, so the Amperian loops will be in the form of circle. The first one, where the point is inside in the interior of the toroid, the radius is given by R1. For a point which is inside the toroid, which is the Amperian loop, is given by 2. Its radius is R2, and for the third point, which is outside, that is the exterior of the toroid, the Amperian loop has a radius R3. So the first condition, we are taking the point in the interior to the toroid. Now the point P lies in the open space in the interior of the toroid. Now we will be using the Ampere Circuital Law. Integration B dot dl is equal to mu naught into the total current threading the loop. Now B dot dl, integration B dot dl, like integration of L gives the total length here. So the total length here of the Amperian loop, you can see here, it is 2 pi R1. So B1 is the magnetic field which we are assuming inside the toroid, that is in the interior portion, open space of the toroid. The value is B1 into 2 pi R1, which is integration of the small length dl. So it is 2 pi R1, the total length, is equal to mu naught into the current threading the loop. The most important part is that the Amperian loop of radius R1 which we are considering here, no current passes through it or threads through it. So that means the current threading is 0. So we write B1 is equal to 0. That is, there is no magnetic field in the interior space, open space inside the toroid. I hope this is clear. Now let us take a point which is inside the toroid. Suppose we are considering a point S inside the toroid and we want to find the magnetic field here. So to do that, what we will do here is we will draw an Amperian loop, as I have already mentioned, the Amperian loop 2 having radius R2. Again we will use the Ampere Circuital Law. Now the point is inside the toroid. Now you can see here, as the Ampere Circuital Law is integration B dot dl is equal to mu naught into the total current threading the loop. So for integration B dl, so integration of dl gives the total length, which is given by 2 pi r2. R2 is mentioned here as r, so it is 2 pi r. Okay, so you need to understand this. In the diagram it is mentioned R2, but we are taking it as R only here. So the formula for Ampere Circuital Law is B into the total length, that is 2 pi r, is equal to mu naught into the total current threading the loop. Now you need to understand here, the cross here represents the current which is going inward. Now we are considering the loop 2. In this loop 2, the dots are not considered. They are outside the loop. Only the cross part is there, that is the current is moving in the inward direction. Now we need to find the value of the current, the total current which is threading the loop. Now in all the turns the current is I. So for every cross there is I current. Now if you have the total number of turns, then multiply that total number of turn with the value of I, that is the current through the single turn, that will give the total current threading the loop. I hope this is clear to you. So capital N represents the total number of turns. It will be multiplied by I and you will get the total current threading the loop, which is N into I. So therefore the value of magnetic field B inside the solenoid at any point, say S, will be given by B is equal to mu naught Ni, that is capital Ni, divided by 2 pi r, where N represents the total number of turns. Now if N is the total number of turns, now you need to understand here one more thing. Suppose small n represents the number of turns per unit length, then this value of small n will be given by total number of turns, we have already mentioned it as n, divided by the total length, and the total length here is 2 pi r. Okay, so this n is the small n, it is the total number of turns per unit length. So number of turns, total number of turns is n, so per unit length the total number of turns will be capital N divided by 2 pi r. So naturally here this value capital N divided by 2 pi r represents the number of turns per unit length. So this can be written here as small n. So we have the final formula for the magnetic field, which is given by mu naught into Ni, where small n represents the number of turns per unit length. So I hope this is very clear to you. Now we are left out with another point, the last point at the exterior of the, that is outside the toroid. So let us see how we are actually calculating the magnetic field. So let's say the point is Q, and that's why the Amperian loop 3 we are considering, which is outside the toroid. Now we all know the Ampere Circuital rule is integration B dot dl, which is B into the total length, is equal to mu naught into total current threading the loop. Now, to understand the total current threading the loop, now the dots and cross both are coming within the loop, Amperian loop, the third Amperian loop which we are considering. That means whatever current is coming out of the plain paper, the same current is entering the paper also, that is entering the cross section. So the net current is 0. So if the net current is 0, that is B into the total length is equal to 0, because mu naught into total current which is threading the loop will be 0. Equal number of current moving out, that is moving in one particular direction, and the same amount of current is moving in the opposite direction. So the net current threading the loop will be 0. So therefore the magnetic field at any point Q outside the toroid will be 0. So I hope this is very clear to you. You can see here, since the current I is 0, that is the total current threading the loop, third loop is 0, hence the magnetic field which is given by B3 here is 0. So go through the video very carefully, and I hope that it will be clear to you in one go only. But still then, if you find any doubt, you must post the doubts so that I can clarify the doubts. Thank you.